It is section 9.4, Deep Learning, Convolutional Neural Networks. In this section, we'll consider deep neural networks. The focus is on understanding core fundamental principles behind the deep neural networks, and we'll apply those principles for the simple, easy to understand the context of the MNIST classification problem. Let's see this example. Here, the MNIST dataset is given. For the dataset, we may build a neural network having 3 hidden layers as follows. The input layer, and hidden layer 1, 2, 3, and the output layer. Assume each of the hidden layers has 30 neurons. Then we can count number of weights and number of biases to teach. For this layer, here, input layer has 28 squared units, and we assume here 30 units. Then number of weights to teach is 28 squared times 30. For this layer, 30 times 30, and again 30 times 30, and finally 30 times 10. Altogether, number of weights is a bit larger than 25,000. For biases, each neuron, each unit has 1 bias, so that here 30 biases, 30, 30, and 10, altogether 100. With this larger number of weights and biases, optimization is not easy. The number of parameters to teach is huge, so that the efficiency is low, and it can have multiple local minima problem, so that the solvability is low. In general, adding hidden layers is not necessarily improving accuracy. In fully connected networks, deep neural networks means that many hidden layers. Deep neural networks have been hardly practical except for some special applications. For this network, along with 30 neurons in hidden layers, the classification accuracy is a little bit better than 98%. It's about 98.5% for the MNIST data set. However, it's strange to use networks of fully connected layers to classify images. Here we have a reason. The network architecture does not take into account the spatial structure of the images. For example, the network treats the input pixels far apart and close together on exactly the same way. What if we use an architecture which tries to take advantage of the spatial structure? Then, can it be better than 99% in accuracy? Here, we'll introduce convolutional neural networks, CNN, which use a special architecture particularly well adapted to classify images. The architecture makes the convolutional networks fast to train. So as a result, we can train deep many-layer networks. Today, deep CNNs are used in most neural networks for image-based recognition and classification. CNNs use 3 basic ideas. local receptive fields, shared weights and biases, and pooling. Let's consider them one by one. Local receptive fields. Okay, this is input layer. Rather than long vector, we put neurons, the units, in this way, exactly the same way as for the images. So there is a 28 by 28 neurons, that is input neurons, and here we'll have the first hidden layer, and here the connection is given in this way. Rather than fully connected the network, we are considering only this small area, so that in this case now 5 by 5, the values will be connected to a hidden neuron. So such a small localized region is called local receptive field. And we use this idea in this way. Okay. Here, and for the choice of a 5 by 5 local receptive field, we choose this field and connect to the first hidden the neuron like that, and by moving one pixel to the right, and again we try to connect that here the field into the next the neuron in the first hidden layer, and moving one more, and then after finish this one, now we start from here. Now go down one pixel and go through, and eventually we'll cover all the image. Then here, for this choice of local receptive field and the choice of movement, and from this 28 by 28, we can have here output in the first hidden layer and 24 by 24 pixels. Here you may think in this way, the center of that one is now moved to the first one, and of course at the end here, center of this one will move to the rightmost one, so that here we are now here we have to delete here 2 rows and 2 columns, so that 28 by 28, in output it become 24 by 24. Okay, so the local receptive field is used in this way. And for this example, the stride length is 1, its movement is 1 pixel at a time. Now you can choose different stride length. For instance, we might move the local receptive field 2 pixels to the right and 2 pixels to the down, and so that in this case the stride length must be 2. Most of the software gives a hyperparameter for the user to set the stride length. The default is 1 in most cases. Okay, now share the weights and biases. Okay, now we'll go back to the picture again. Okay, right now, here connection from this the small region to the unit here, and again this region to the next unit. But this connection is not independent. In fact, these are the same by using same weights and bias, and we are connecting from this field to the first one, and same weight and same bias, and using them, we are connecting from this to that. That is the idea of shared weights and biases. Okay. Now, so that here, through so that here now, that one will be used for every the receptive field, but in any case over there, the W and B will be the same. So it can be written in this way. So from A0, the activated value, so eventually if we are using image values, then there's A0. Now A1 is made. That is made here, like this one. And W is, in our example, is a 5 by 5, and the operation is like a convolution. And now bias, the same W and same B is used to all over the image. So it is in a form of a convolution. So that's the reason the network is called a convolutional network. And sometimes we call the map from the input layer to the hidden layer feature map. Okay. So this connection itself is a feature map, or sometimes we call this output is a feature map. Okay. Now, suppose the weights and bias are such that the hidden neuron can pick out a feature, for instance, vertical weight in particular local perceptive field. For example, now right part over there is positive 1 and left part is negative 1. Then it is a kind of a measuring horizontal derivative, and so that it can pick the vertical line, because around there the derivative will change, so that here it is possible. The ability of picking up a feature also likely to be useful at other places in the image, so that it is useful to apply the same feature detector everywhere in the image. So such weight and bias defined in the feature map is called shadow weights and shadow bias. And here the set of shadow weights and bias defines clearly a kernel or filter. Yeah, that is so that these two makes a convolutional kernel or a convolutional filter. Okay. Now, each kernel or each filter is making a feature map. And now, and as explained over there, is a sort of the translation invariant, so that it is well adapted to the translation invariant of images. Here, translation invariance means here, move a picture of a cat a little bit a different position, and it's still an image of a cat, right? So that in location, so in a sense, location invariant feature is captured, so that eventually the network can be much more powerful. So rather than location-based, here in fully connected case, location is changed, then it is not well working. So that you have to choose the data very carefully. But along with the CNN, now is trying to get feature so that eventually it becomes translation invariance, right? Okay, and here we considered a feature map, but it's a single localized feature map is not really good enough. So to make it more effective, we need more than one feature map. So here, and in reality, we have to make several different feature maps. In this picture, right now, we have 3 feature maps. But usually, a CNN is built with more than 10 and sometimes more than 50 feature maps. And these pictures show that when we train CNN with 20 feature map, then that is the feature map practically obtained through the training. So it's the real trained data here. And now this is a 5 by 5, but the local research field can be 3 by 3 or 5 by 5, 7 by 7 or 9 by 9. But for this one, it is a 7 by 7, and that is the practical the feature map, 20 of them. Okay. Here, the big advantage of sharing weights and biases is that it hugely reduces the number of parameters involved in a convolutional network. For example, here we can compare in this way. Now, convolutional neural network, each feature map requires train and a convolutional filter, 5 by 5, and that is bias, and 20 the features, so that now this whole thing is 520. But if you try to get here 20 neurons in the first hidden layer, then fully connected network is requiring 28 squared times 20, and along with the bias, now we have more than 15,000 parameters to teach, so that the shared weights and biases will make the network and much better to teach. However, anyway, the next connection is from the output of this convolutional neural network, so that if you are choosing, for example, here now 20 of them, then each one is 24 by 24 times 20, so that that is really a huge number. And from that number of the neurons, the next one, for instance, now is fully connected, then you have to train all the weights and biases for that connection, so that here the next layer is another story. But from here to there, along with this shared weights and bias, it becomes much more efficient. Okay, now the final idea is pooling. CNNs also contain pooling layers. This is simply the shrinking the information. For example, now that's output of the convolutional layer. So it has a 24 by 24 neurons. Now we try to simplify the information by taking here 2 by 2 becomes 1. Here that is 2 by 2 becomes 1. So that after pooling, the image becomes now 12 by 12. So that is here the pooling. And yeah, 24 by 24 is, in a sense, not necessary. It's too large yet, so that we try to select the information in simplifying some many values, so that we try to get very simpler the information here. That is idea of pooling. Okay, here, along with this picture, it can be explained quite nicely. Original input is 28 by 28. Now, along with 3, the future map, we have 3 times 24 by 24. And 2 by 2 pooling makes 3 times 12 by 12. In this way, we can simplify the information. Here, types of pooling, there are 2 here. Now, it is the most popular 2. Max pooling, that means that out of 2 by 2, you can take the maximum value. That's max pooling. And L2 pooling is now for the 2 by 2 values, try to get L2 average. So it is average pooling, and this is a maximum pooling. But also you can choose this size. Rather than 2 by 2, you can use now 3 by 3. Then the output will be now 3 times, 3 times shrinking, so that 3 times 8 by 8. Right? In this way, you can simplify the information. Okay, that's 3 the basic ideas for CNN, and in the second part, we'll try to design the CNN, so that we'll try to consider the reality of CNN. Thank you.